So today we're going to talk about one particular second degree linear model. We're going to talk about a spring mass system. All right, so the idea today is we have a spring, and from that spring we are suspending some mass. And we're going to take the spring and we're going to stretch the mass above or below the equilibrium position and let it go. And it's going to move. So we want the equation that describes that motion. So for the spring, we have Hooke's law. And Hooke's law says that the force exerted by a spring is in the opposite direction of motion, or I'm going to say of elongation. And is proportional to the elongation. In short, F equals negative Ks, where K is our spring constant, which is greater than 0, and S is the elongation. So if we pull the mass below the equilibrium position, the spring is going to exert a force upward, and if we push the mass upward above the equilibrium position, the spring is going to impart a force downward. So now we're going to apply Newton's second law. If we pull the mass down or push it above equilibrium position and let it go, it's going to start moving. So we have some acceleration. So we're going to apply Newton's second law. And we have the mass times the acceleration, dt squared, is equal to negative kx. And I'm going to rewrite this. And this is just mainly for convenience when we actually solve this equation. We divide everything by the mass plus omega squared x equals 0, where omega squared is k over m. So this differential equation, when we're talking about a spring mass system, I'm having trouble writing omega there. There we go. This describes what we call simple harmonic motion. And we know the solution to this. We could probably solve this equation without even writing anything down at this point. If we write the auxiliary equation, that is m squared plus omega squared equals 0. This is why we wrote omega squared. So m squared equals negative omega squared, and m equals plus or minus I omega. So we get, what's that? Yes, we've done a few homework problems that kind of preface what we're talking about today. So we get our solution, x of t is C1 cosine omega t plus C2 sine omega t. And this is called simple harmonic motion. The period t is 2 pi over omega. And if you remember from pre-calc, we talked about the period of these functions. We call this b, 2 pi over b. And the frequency, and the period is the time to complete one cycle. So the period could be 3 seconds per cycle, something like that. And then the frequency is 1 over the period, which is omega over 2 pi. And this is cycles per unit time. And for everything we do today, we're going to say the positive displacement is the distance below equilibrium. So now we have a mathematical description of what we've seen probably for most of our lives. When you pull a spring, it kind of bounces in this nice periodic motion. And of course, we're ignoring the internal friction of the spring and all that kind of thing. When we find our constants, if we have an initial value problem, when we find the constants, we call that equation the equation of motion. So once we determine our constants, this would be our equation of motion for simple harmonic motion. Now, because our solution has a sine and a cosine, we can't really, looking at this equation, if we want to know the amplitude of the oscillation, it's not immediately apparent from here. We can show, you can rewrite this equation, you can do some work to this, and they do this in the book. They talk about something called phase angle, which I think is a little beyond what we need to talk about. Well, you can show that the amplitude of oscillation is, right, A is a square root of C1 squared plus C2 squared. So you can rewrite that equation in a way. It takes a little work with trig identities and various things, so that the constants in front of the sine and cosine are both the same. And when you do that, that amplitude is the square root of C1 squared plus C2 squared. And I think there's one homework problem where it asks you to find the amplitude of the oscillation. So there's our kind of our first application of a second order linear homogeneous differential equation with constant coefficients. Isn't that nice? Well, now we're going to add a little bit more reality to this, we're going to talk about damped motion. So damped motion means there's some kind of force that is acting against the motion, some kind of friction, some kind of something. All right, so our assumption we have a force proportional to the velocity. Acting in the opposite direction of motion. So that could be friction. We could assume that the friction is proportional to the velocity. It could be some kind of self-friction inside the spring that is acting against the motion. Often, and this is a, it can be a very simplifying assumption, because friction for your forces could be proportional to some other quantity of the velocity. It's not unusual for the friction, is it air friction? Often is proportional to the square of the velocity. So that makes this equation that we're going to write next much more difficult. All right, so from Newton's second law, we can now say that m d squared x dt squared equals minus kx for a spring constant minus beta dx dt, where beta is our proportionality constant for this force that's acting in the opposite direction of motion. Or we'll rewrite this as and I'm going to divide through by m, put everything on one side of the equation. We get d squared x dt squared plus beta over m dx dt plus k over m x equals 0. And we're just going to rename these constants just to make our algebra nicer. So we get d squared x dt squared, the acceleration, plus 2 lambda dx dt plus omega squared x equals 0, where beta over m is 2 lambda and k over m is omega squared. And the 2 lambda and the omega squared just make our algebra come out nicer. So our auxiliary equation is, in this case, m squared plus 2 lambda m plus omega squared equals 0. And we're going to use the quadratic formula to solve for m. So I get m1 equals negative lambda plus the square root of omega squared minus, lambda squared minus omega squared. So we use the 2 lambda so we can divide that 2 out. And m2 is negative lambda minus the square root of lambda squared minus omega squared. So yeah, the 2 lambda here lets us,
Oh, I see.
so we don't have the fractions in there. So just like before, when we first started solving these second order linear differential equations with constant coefficients, we have three possibilities. So we have three cases, depending on the sign of lambda squared minus omega squared. Now we can see that all the solutions are going to have a factor of e to the minus omega t. So we're going to have some kind of decaying factor in time. So with that friction, eventually that motion slows down and the displacement approaches zero as t approaches infinity, which makes sense with friction. So our three cases. The first case is if lambda squared minus omega squared is greater than 0. So we call this system overdamped. That means that beta is large relative to k in order to get lambda squared minus omega squared greater than 0. So our damping force is large compared to the spring constant. What large means? Large enough to make this greater than 0. And we get, in this case, x as a function of time is e to the minus lambda t from this times c1 e to the square root lambda squared minus omega squared t plus c2 e to the minus lambda squared minus omega squared t. And basically we have some kind of decaying exponential. If we make a graph, a typical graph of an underdamped system, if that's x and that's t, it might just look like this, or it could do something like this. So, sorry, overdamped system. For an overdamped system, we really don't get much oscillation. The next case is when lambda squared minus omega squared equals 0. We call this critically damped. In this case, a slight decrease in damping force would result in oscillation. And vice versa, a slight increase would give overdamping. In this case, our solution, x of t, is e to the minus lambda t times c1 plus c2t. Since we get repeated roots, we have to add that t for our second solution. And a graph of critically damped motion, if that's x and that's T. Could have something that looks like this, or something that looks like this. And there is at most, for critically damped motion, one maximum. So in this case, the mass would pass through the equilibrium position at most one time. We started here at most one time, and then it would decay. And this is when x prime of t equals 0. How we always find the maximum, we set the derivative equal to 0. And then finally, if we have lambda squared minus omega squared less than 0, so we get a negative quantity under our radical, we call this underdamped. And this is when we get oscillatory motion, because we get the imaginary portion gives us the sines and cosines in our solution. And an underdamped system is that beta is small compared to k. How small? Small enough that this quantity is less than 0. So the roots of our auxiliary equation are complex. We get sines and cosines. We get x of t is e to the minus lambda t. We have all of that in all of our solutions. And then we get c1 cosine square root lambda squared minus omega squared t plus c2 sine of that quantity square root lambda squared minus omega squared t. And I'm going to graph this. This would be undamped motion. So undamped, we just get nice oscillation. For underdamped, we would have some kind of decaying exponential. That is let me undo that. I want to do this. Make a better drawing. So this would be underdamped. And then critically damped would look something like this. We get one oscillation and then decay. So now all those complicating factors that we ignore in introductory physics, we've taken into account in about 10 minutes. Now the really complicated ones we haven't talked about. If I go back here, if this is proportional to the square of the velocity, then we have a nonlinear second order differential equation, and that's much more difficult to solve.
Thank goodness it isn't.
What's that?
Thank goodness it isn't.
All right, the last thing that I want to talk about today, which brings up an interesting topic, is driven motion.
Who gets to drive? Wait, Mr. Beaver, are you still allowed to drive after the crash?
Yes.
I wanted to make sure. Sometimes. That's how bad the crash.
So for this equation, we have some kind of force. In addition to all the other ones, we have some kind of force driving the motion. So the driving motion, if you think about like someone on a swing, the parent is pushing at each end. So that's driven motion. You have something that's adding some kind of, or subtracting some kind of force at regular periods, or irregular periods also. So if we have a driving force, our equation from Newton's second law becomes our force here equals negative kx minus beta dx dt plus some f of t. We have some force that is as a function of time that's pushing, pulling something on our mass. So we can rewrite this. I'm going to divide, like we did before, divide by the mass, put all the functions of x on one side of the equation, 2 lambda dx dt plus omega squared x equals capital F of t, where 2 lambda is beta over m, omega squared is k over m, and f of t is little f over m. So now we have a non-homogeneous second order linear differential equation with constant coefficients, which we also know how to solve. Depending on this driving function, we can use undetermined coefficients. It's a nice function, one of our family of functions that works. If it's something else, we can use variation of parameters. Our auxiliary equation for the solution of this equation is the same. We have the same things happening there. We just have our particular solution that comes out of this driving force. So I'm just going to say can use undetermined coefficients. Or variation of parameters. To find our particular solution. In this case, so really the solution of this depends on what our driving force is. The complementary solution is one of those 3 options that we just talked about. And then we're going to have a particular solution that depends on this driving force. A solution that decays in time. Time. So we're saying x of t approaches 0 as t approaches infinity, is called a transient solution. A solution that does not decay in time is called a steady state solution. So if we had something like, we solved an equation, we get C1 e to the minus t cosine t plus 5/2 sine t. This is our transient, and this is our steady state. So an interesting thing happens in particular situations with driven motion. And that interesting thing is resonance. And if you've taken physics, if you've taken science, you've probably heard of resonance before. We're going to talk about it mathematically. If we have our equation d squared x dt squared plus omega squared x equals f sub 0 sine gamma t. So I think we did a homework problem like this. I know we did a homework problem like this at least somewhere. So we know our auxiliary equation is m squared plus omega squared equals 0. So m equals plus or minus I omega. So we get sines and cosines. So our complementary solution is C1 cosine omega t plus C2 sine omega t. And using undetermined coefficients, we would say our particular solution is A sine gamma t plus B cosine gamma t. And we can take our derivatives. This is not a difficult undetermined coefficients problem. We would find we see that A is 0 and B is f sub 0 over omega squared minus gamma squared. So x of t is C1 cosine omega t plus C2 sine omega t plus f sub 0 omega squared minus gamma squared sine gamma t. Anybody see anything interesting or potentially problematic here with this solution in terms of the relationship between gamma and omega? Yeah, if gamma equals omega, what happens? We our x of t approaches infinity. This is what we call pure resonance. So a resonant frequency is the frequency that gives us an output that gets very, 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 very large in time. In this case, our resonant frequency would be omega. When we drive the system at its natural frequency that we get from the solution here, when we drive the system at its natural frequency, the amplitude continues to increase over time. And if you've seen the film video of Tacoma Narrows Bridge that like goes crazy and collapses, the wind was driving it essentially at its resonant frequency, and causing the amplitude of the oscillations to grow in time until it fell down. So that's a bad thing. Yeah, if you've never seen it, you should Google it. It's pretty cool to watch. Not right at this second. We're almost done here. Tacoma Narrows Bridge. I'm surprised you haven't seen it in some science class. So the resonance frequency is the frequency of the complementary solution. In this case, it's omega over 2 pi. We can find the limit as gamma approaches omega. So this is our function. We're going to apply L'Hopital's rule and differentiate with respect to omega. I'm just going to say LH rule, L'Hopital's. And in the case where we have our initial conditions, x0 equals 0 and x prime of 0 equals 0, we end up with x of t equals f sub 0 over 2 omega squared sine omega t minus f0 over 2 omega t cosine omega t as omega approaches, gamma approaches omega. You have there's one homework problem. The last homework problem in this section is basically doing the math to show all of this stuff. So you use undetermined coefficients, use your initial conditions, and then use L'Hopital's rule, differentiate with respect to gamma to find our limit. And we can see as t approaches infinity, because of this t term, our x of t, our output, is going to grow in time. All right. So now we know everything we need to know about spring mass systems in a mathematical sense. When you were solving these differential equations, so if some of the homework problems ask you to give you a mass, give you a spring, and you find the spring constant, etc., and you come up with a solution, In general, when we solve, I'm going to suggest write this equation mx double prime plus beta x prime plus kx equals, if we have the driven motion, f of t. Solve it from there, because you can just write your auxiliary equation and come up with your solutions. Don't try to do your, I think it's easier to do the solution from here than trying to say, oh, well, 2 lambda is beta and omega squared is k over beta over m, k squared, omega squared is beta, k over m, and substitute that way. Just solve the equation the way we know how to solve it. I think that makes more sense. I think it's a little easier than just going through the brain power of doing those substitutions. And also, so we are aware, and this is in part because of how our book does this, often the units are given to you in pounds. Pounds are a unit of force. So if we want our mass, if they say, the problems will also often say the mass weighs 5 pounds. That's in part because of how imperial units work. Our weight, sorry, our mass is going to be our force divided by the acceleration of gravity by Newton's second law. In this case, our mass is going to be our weight in pounds divided by 32 feet per second squared, which is the acceleration due to gravity in imperial units. And the units for mass in the imperial system are slugs.
What? It's a slug.
So instead of a Newton, we're talking about slugs. Now, the units of our spring constant will be pounds per foot. Apparently, according to this book, engineering units always use feet as a unit of distance. So you're going to have to convert sometimes you'll have to convert some units from inches to feet in these problems. So our units of K are pounds per feet. This unit needs to stay in pounds because multiplying K times X gives us a force. Because this equation is all about forces. This is the force associated with acceleration. This is the force associated with the velocity. This is the force accelerated with the elongation of the spring. So the mass needs to be in units of slugs if you're given the weight in pounds, but the units in K will still be pounds per feet. So when you're doing these equations, keep that straight in your constants. All right. Questions? I always thought when I was a student that, to me, springs made way more sense if I could apply the differential equations. It's like, oh, that makes sense. That's why they work the way they do. Where if it's just explain, oh, you have this, it's like you get a lot of hand waving, oh, this happens, oh, this is what's happening. We can see the solution. The solution is sines and cosines. Oh, when we have a friction force, it decays. That comes right out of the math. To me, that was interesting. So I made, I think, I'm not sure if have I uploaded it to Schoology? I think I uploaded it to Schoology. I made some amendments to this homework because one problem has like A through K or something, and I want us to skip some of those. So let me get the right thing